Okay, so it's been a little bit since I've done a video with y'all, but since I am out and we have no extra days, you're going to have to watch your very last lesson on video. So luckily it's pretty simple. We're talking about similar solids, so we're going back to similar figures. So remember, similar solids have exactly the same shape. Well, so they have exactly the same shape, but not the same size. Two solids are similar if the ratio of their corresponding linear measurements are equal. So what that looks like. So we have types of linear measurements. So let's talk about the types. And I'm going to type them because I am terrible at writing this quickly. So types of linear are the length, the width, the height. The slant height is linear. So basically anything one-dimensional. The perimeter, the radius, the diameter, and the circumference. So let me move this one down here. And make that work in there. So there we go. So these are the things that would be considered linear. So let's take a look at some examples. So let's say, directions say, determine whether these solids are similar. So if yes, give the scale factor in simplest form. So remember, your scale factor is new over old. So we're going to be looking at new over old. So always remember that usually the first figure, I think, is my original. So this would be my original, and this would be the new one. So remember, scale factor. So scale factor is a K, and it's new over old. So new over old. All right. So let's look and compare. So the first thing I'm going to compare their heights. I know both heights I'm going to compare. So new over old. So that would be 1/4. And then I'm going to compare their widths. So new over old would be 2/8, which reduces to 1/4. And then I'm going to compare their lengths. So new over old would be 5/20. So that would be 1/4. Since they have all three same scale factors, then yes, they are similar. The scale factor is 1/4. So now we'll do another one. So now looking at number 2, I'm going to change the color so we can separate between 1 and 2. All right, so first thing I'm going to do, this is the original, this is the new. So I'm going to compare their heights. So this would be new over old. Then I'm going to do 10/6. Then I have 10/6. And then I'm going to compare 10/6. 10/6. Well, obviously these two are going to reduce to the same because they're exactly the same. So this would be 2 goes into that 5/3. 5/3. Now this one, 4 will go in 3 times to 2 times. So even though these two are the same, this one is not. So these are not similar. And then the last one you can compare. So I know that this diameter is 24, so the radius is 12. And then this radius is 10. So this is my new, this is my old. So this would be 10/12. And then I would compare their heights. This height is 25, this height is 30. 25 to 30. So reduce 2 will go into that 5 times. 2 will go into that 6 times. 5 will go into that 5 times. 5 will go into that 6 times. So since they are the same, yes, and the scale factor is 5/6. All right, so now let's compare. So this is where it gets fun. So if two solids are similar with a scale factor of A to B, so a scale factor of A to B, or maybe we're going to write it as A over B, then their volumes and their surface area ratios are as follows. A squared to B squared, or maybe we write it as A squared over B squared. Their volume would be A cubed to B cubed, or maybe we write it as A cubed over B cubed. So basically, you take the original scale factor, and if you square it, that's the area scale factor, and if you cube it, it's the volume scale factor. So I'm going to show you how this works. I call this a save table. And you can just do little mini tables for your problems. It's not really difficult, and that's a horrible line. Okay, so what we're going to do is we're going to identify the scale factor or their ratios for each pair. So what I'm going to do is, okay, this is my new, this is my old. So this would be 3/6. So 3/6 reduces to 1/2. So my scale factor is 1/2. So to get to the area scale factor, because this is just a scale factor table, so 1/2, you square it. So this would be 1/2 squared, which would be 1/4. So now my area scale factor is 1/4. The volume is to take this and cube it. So now you've got 1/2 cubed. 1 cubed is 1, 2 cubed is 8. So your volume ratio is 1/8. Or 1/8. So you always have to have this one first. If you don't, then you have to work backwards, which I will show you how that works. And it's actually pretty simple, but the table helps. So what I'm going to do is I'll just use this as my SAV. All right, so I'm going to compare. So this is 6/4. So my scale factor is 6/4. 2 goes in 3 times, 2 goes in 2 times. So my scale factor is 3/2. Take this and square it. So this is A over B. This is A squared B squared. So that would be 9/4. And this is A cubed, which means 3 cubed. So 3 cubed is 27 over 2 cubed, which is 8. So my scale factor, 3/2, 9/4, 27/8. Now, if I give you, so here, let me back up for a minute. On number 4 and number 5, I gave you a linear dimension. So I gave you a linear, so this is where we started. Now I'm going to give you the surface area or the volume. So now you'll be starting in a different column. So let me show you. So again, I always just do SAV for each one. It just doesn't take but a second to write those. And to make this easier, it's worth it. So what I noticed is they gave me surface area. Since they gave me any form of area, that means 4/25 goes in the area column. So if this is your A and this is A squared and this is A cubed, then to go from this column to this one, you have to take the square root. So the square root of 4 is 2, and the square root of 25 is 5. So now my scale factor is 2/5. My area scale factor is 4/25, and my volume scale factor is still going to be cubed. So 2 cubed, and 5 cubed. So this is 8/125. Now you're going to need these because you're going to be finding missing pieces and using proportions as we go on. All right, so let's look at number 7. Now they gave us volume. So I'm going to do the SAV. So since they gave me volume, I'm going to put these two numbers over here. But the first thing I want to do, I'm going to do 384 over 162. I'm going to see if they reduce in my calculator first, because you never want to put them in this column until they're reduced, because this is actually a ratio. So 384 divided by 162, math, enter, enter. And that is 64 over 27. So this is 64 over 27. So we're going to start here. Now to go from here all the way back, so remember this is your cubed column. So that means to go this way, you have to take the cube root. In your calculator, if you press math, you'll see that number 4 will take the cube root of a number for you. So if I did the cube root of 64, so if I did 464, I will find out that the cube root of 64 is 4, and the cube root of 27 is 3. So now this scale factor is 4/3. Now if I square it, because remember this is your squared column, 4 squared is 16, 3 squared is 9. So now I've got 16 over 9. So you can start at the beginning and go forward. You can start in the middle, go back, then forward. Or you can start in the very last column, go to the beginning, and then go this way. So number 8 says 2 surface areas. So I've got 375 over 960. So I'm going to reduce them. I forgot to write this up here. I'm sorry. Okay, so I'm going to reduce these two. So 375 divided by 960. And then I'm going to do math, enter, enter to get my decimal, or to get my reduced fraction. So 25 over 64. So this, so I did SAV. So this is going to be 25 over 64. So I'm in the middle, so I've got to go back here. So that means I have to take the square root. So the square root of 25 is 5. The square root of 64 is 8. Now from here, I can go here. So you had to do this first. Let me do this second. So 5 cubed is 125. And 8 cubed is 512. So these are the 3 fractions that go here. So we've got 5 over 8, 25 over 64, and 125 over 512. So that is how you find your ratios. Now we're going to look at a handful of these. Probably won't do every single one of them, but we'll do a handful of them. So let's see what happens. So it says solid A is similar to solid B. So it doesn't matter what the shape is. We just know they're similar. It says the ratio of the height. So since they're talking about height, they're talking about the one dimension. So they're saying, so if I did SAB, so this is why I was saying this table is super handy. So they're saying that the height of solid A to the height of solid B is 7 to 3. So that means this would be 49 over 9. And this would be 7 cubed, which is 343. And 3 cubed, which is 343, which is 27. So here are my scale factors. So it says find the ratio of the volume. Well, since they're asking me to find the ratio of the volume, that's the column they're asking me to find. If you just fill out the table, then you have all the answers to any question that they may be asking. All right, so let's try another one. So cone A is similar to cone B. The ratio of their surface area. So if I set up my table, so they're telling me the ratio of the surface area. So they're saying 16 to 1. Well, I've got to go backwards. So I've got to take the square root. So the square root of 16 is 4. The square root of 1 is 1. So that's, then if I go from here all the way to here, 4 cubed, so 4 raised to the 3rd power is 64. And 1 cubed is 1. So you always go backwards and then you'll go forward. So it says find the ratio of the radius. Well, remember the radius is one dimensional, so that means first column. So the answer to the question would be 4 to 1. So the ratio of the radius is 4 to 1. It's pretty simple. If cylinder A and cylinder B are similar, and cylinder A has a diameter of 24 and cylinder B has a diameter of 30, since diameter is one-dimensional, then I want to put it in the one-dimensional column. So this would be, since I listed, I'm just going to say 24 to 30. So I want to reduce this. So 24 divided by 30, math enter, it's 4 over 5. So now this is squared, so this would be 16 over 25, and this is cubed, 64 over 125. So take what they give you, put it in the appropriate column, find the other two columns. Now it says, what is the ratio of volume? Well, they're wanting this column right here. So now you have, if they had wanted area, then you would have had that one as well. So now you have them both. All right, this one says Pyramid A and Pyramid B are similar. They have a volume of 648 and 1029. So 648 to 1029. So I'm going to see if these will reduce. And they do. They reduce to 216 over 343. So these are volume ratios. So I'm going to do SAV. So this is going to be 216 and 343. So now I've got to go from here all the way back to the beginning. So I have to take the cube root. So the cube root, so math 4, 216 is 6. So the cube root of 216 is 6. And the cube root of 343 is 7. And now I can square both of these to go back this direction. So this would be 36 over 49. And they're asking me about the ratio of area. So they are asking me about this column. All right. So now, let's see. All right, that took care of that. So now let's talk about the effects of changing dimensions. These are pretty easy because what's going to happen is, all right, let me scroll through here. I apologize. All right, so if the dimensions of a solid are multiplied by a scale factor of A, then the surface area is a squared times the original, and the volume is a cube. So this goes back to our SAV table. So it says if the dimensions of a figure are doubled, how many times will the surface area be? How many times larger? So all you do is you take how you're changing it. So I'm going to double all of the linears, okay? So it says the dimensions of a figure. So if it's a cylinder, I'm going to double the radius and I'm going to double the height. So if I double the radius and double the height, that means I have to square it. So that means the new one will be 4 times bigger, because it says how many times larger will it be. So we're looking at surface area example. So we're talking about squaring something. It says the surface area of a figure is 62. If the dimensions are multiplied by 5, what will be the surface area of the new? So what you do is you take how you're changing it. So I'm multiplying everything by 5. And since we're talking about area, we square it. So it's 25. So that means it's going to be 25 times bigger. So you take your original and you multiply it by how many times bigger? So 62 times 25. So the new area will be 1,500 150 centimeters squared. And then you would do the same thing with the others. All right, so it says the surface area of a new figure, or sorry, the surface area of a figure is 736. Now I'm changing the dimensions by 1/4. So you're going to take your 1/4 and you're going to square it. So now it's 1/16. Now you take your original area, so the 736, and you multiply it by 1/16. So 736 times 1/16 means 46. So that would be 46 inches squared would be your new area because it is 16 times smaller now because it's 1/16. Cone A is similar to cone B. If cone A has a surface area of 1422 and cone B has a surface area of 158, how many times larger is cone A than cone B? So what we're going to do is we're going to think about it just like the SAV table. So we're going to figure out what is our scale factor. So 1422 divided by 158 is 9/1. So that means that your, it just wants to know how many times larger is the cone. So if my SAV table, so since they gave me area, that means this is 9/1 because I'm looking at area. So that means if I go back to here, I would have to take the square root. So that would be 3/1. And then to go this way would be 27/1. So if they're asking me how many times larger, well, if the area is 9 times bigger, then that means the whole figure is 3 times bigger. So this would be 3 times bigger because you needed to get the actual scale factor, which would be this column here. Because I needed the actual scale factor. So reduce their area and then go backwards to get the actual scale factor. Same thing works with volume. It works the same way. So if the dimensions of a figure are multiplied by 4, so now I'm changing it by, I'm changing it by 4. So that means 4 cubed, which is 64. So that means it is 64 times larger. So I'm going to put 64 times larger. And this is our A cubed example. So we're looking at our V column. So the volume of a figure is 110.5 feet cubed. If the dimensions are doubled, so doubled means that, and since we're talking volume, we're talking cubed, which means 8 times bigger. Well, if the volume was 110.5 and it's now 8 times bigger, then that means 884 feet cubed is your new volume. The volume of a figure is 972. If the dimensions are multiplied by 2/3, so now we've got 2/3 and we're talking volume, so we're cubing. So that means 8/27. So take your original volume, 972, and multiply by 8/27. So 972 times 8 divided by 27. So that's 288 meters cubed. So since it's 2/3 smaller, then the volume will be 8/27 smaller. So it's definitely going to be smaller. All right, and then the next one. Solid A is similar to solid B if the volume is 21 and the volume of solid B is 4536. So what I'm going to do is find their ratio. So 4536. So 21 divided by 4536. Math enter. So that's 1/216. So this is my volume scale factor. So basically, if they give you 2 volumes or 2 areas, you're going to need to do the table. So to get the actual scale factor, I have to go back. So you're going to need to take the cube root. The cube root of 1 is 1. The cube root of 216 is 6. So your actual scale factor is is 1/6. So that means it is 6 times smaller because 1/6 is a small number, where 6/1 would be a big number. So it is 6 times smaller. All right. So what happens if you only change one dimension? So like if you have a can and you know how some of the energy drinks, are there a different size can than like sodas, like a Dr. Pepper or a Coke? They're just in 12-ounce cans, where like Monsters are much larger. I don't know exactly, but I do know that their radius and their heights are different. So what's the difference in their volume? What's the difference in their surface area? So changing only one dimension means that the figures are not similar. Okay, so they are not similar. Because if I only change one thing, then they're not similar. In this situation, you're going to choose test values. And you're going to calculate both the old and new surface area, and then compare your answers. So how many times larger is the volume of a cylinder if just the height is doubled? So, for example, it says we have a cylinder. So let's say that I have, so volume is pi r squared h, because we are still talking about volume, and this is the formula for the volume of a cylinder. So it says to choose test values. So let's just say that our original, the radius is 1 and the height is 1. Obviously, you're going to choose easy numbers. So volume is pi r squared h. So 1 squared is 1, 1 times 1 is 1, and 1 times pi is 3.14. Okay, now if I choose to, it says to double the height. Okay, so we're going to double the height. So now the radius is 1, and now the height is 2. So now I've got volume is pi r squared h. 1 squared is 1. 1 times 2 is 2. And 2 times pi is 6.28. So now compare. What do you notice? Well, I notice that the new volume divided by the old volume is 2. So it is 2 times bigger. So clearly you're going to want to choose like 1s and 2s to be your test values, because it's easier that way. How many times larger is the volume of a square pyramid if the base edge is tripled? So think about, we've got volume is base times height divided by 3. So if it says the base edge is a square, so the base is a square. So that means that my big B is, let's say that the sides are 1. So for this one, we're going to say the sides are 1, and we're going to say that the height is 1. So this would be 1 squared, which is 1, and our height is 1. So this would be 1 times 1 divided by 3, which is 1/3. So the volume of a square pyramid with base edge of 1. So now they want me to triple it. So now my new base edge is 3, because 1 times 3 is 3. The height is still 1. So now I'm going to do the same thing again. So now big B is 3 squared, which is 9. The height is still 1. So now I've got base times height divided by 3, because that's the formula. So 9 times 1 is 9. 9 divided by 3 is 3. So now my new volume is 3. So doing new over old, so new over old, trying to get our scale factor. The new volume is 3. The old volume is 1/3. So in the calculator, do 3 divided by 1/3, and you get 9. So that means if you, if you how many times larger is the volume? Well, if the scale factor is 3 times bigger, then your volume is going to be 9 times bigger. So we're looking at 9 times bigger. So figure out the formula you're going to use and plug in super simple numbers. How many times smaller is the surface area of a sphere if the radius is multiplied by a half? So we know that surface area of a sphere is 4 pi r squared, and we are almost done, so please bear with me. I know 30 minutes is a long time. All right, so first thing I'm going to do, I'm going to choose my first radius to be 2. And I'm choosing 2 because they're saying it's half, so I want to be able to take half of something without having decimals. So my original here, so we're going to have surface area is 4 pi r squared. So 2 squared is 4. 4 times 4 is 16 pi. And then my new one, if I take half of this, the new radius is 1. So now I've got surface area is 4 pi r squared. 1 squared is 1. 1 times 4 is 4 pi. So now my area is, so this was my original, and this is my new. So how many times smaller? So if I did new over old, so new over old, so 4 pi over 16 pi, let's cancel. So 1/4 is the scale factor, so that means 4 times smaller, because my scale factor is smaller than 1. All right, I believe these are our last 2. So I didn't think I was going to do all of them, but I feel like maybe with me not being there, we need to do them. How many times smaller is the surface area of a cube if the side length is multiplied by 1/4? So a cube, so think about a cube. A cube is the surface area is going to be length times width times height. So how many times smaller? Oh, no, that's volume. Let me back up. So we could do the PBH, but there's actually a special formula for surface area of cubes, and that formula is 6 times s squared. So sometimes when things are like regular, there's special formulas. Take advantage of those because they're easier. All right, so the first thing I'm going to do, my first one, I'm going to choose the sides to be 4. So my original would be 6 times 4 squared. So that would be 16 times 6, which is 96. So my surface area is 96. And now for the new one, since it's a 1/4 smaller, that means my new one, so this is original, this is new, would be 1 because it's a 1/4 smaller. So now it's going to be s squared. Oops, sorry. So surface area is 6 times s squared, which would be 6 times 1 squared, which would be just 6. So now if I did new over old, so 6 divided by 96, math, enter, it's 1/16. So that means 16 times smaller, because my scale factor is smaller than 1. All right, so how many times larger is the volume of a cone if the radius is multiplied by 6? So how many times larger is the volume of a cone? So the volume of a cone is pi r squared h over 3. So my first radius, so since the formula calls for a radius and a height, and it says you're only changing the radius, so since the radius is 1, I'm going to make the height 1 also. So now the original, or the old, would be volume is pi r squared height over 3. So when I go through, I get 1 pi over 3. the new is going to be, well, let me see. It says that the radius is multiplied by 6. So now my radius is 6, but my height is still 1. So you're taking a can and you're making it wider, but you're not changing the height. So pi times 6 squared times 1 divided by 3. So that's going to be 36 pi over 3, which is 12 pi. So now, the last thing you're going to do is you're going to do the new over old. So your new volume divided by your old volume is, so the pi's cancel. So 12 divided by 1/3, sorry, I forgot my 1 there, is 36. So that means it is 36 times bigger because your scale factor is bigger than 1. And I do want to make you note one thing. You can just write it down here at the bottom of your paper. If you were changing like 2 dimensions, like let's say that let's say you change the radius. So let's say the radius is 6 times bigger. And let's say your height is 2 times bigger. So what if you changed them both? Then that means you would just multiply these 2 numbers together. So the whole thing would be 12 times bigger. So that's kind of another way to think about it. All right, so we will go over this in a little more depth. Please make sure that you've done the homework and that you've attempted, because there will be a quiz when I get back. See y'all later.